everyone. It's an amazing time to be alive. We have an incredible opportunity to make our data more useful than ever. And I am, of course, talking about machine learning and artificial intelligence. So why don't we just dive right into it, see what it looks like when an AI is learning. So it's going to be learning to play this Atari slider game, Breakout. And its entire objective here is to get its score to go up as quickly as possible. When it just starts out, it is playing, if you will believe it, worse than I play. But give it a little while, and it is flawless. Look at that, it's even taking some fairly steep angles there. Pretty cool. And then a little longer, and something amazing happens. This little bundle of math and joy is going to discover strategy. How many of you play like this? Let's watch it. It's going to dig itself a little tunnel there on the left, and check out that score go up really quickly. I used to say better than human when I would describe this, but then I gave this talk in Tokyo, and they're like, what do you mean better than human? I mean, come on, we all play like this, right? So it's pretty cool stuff. Seems like magical magic, and you might be dazzled. Let's take us down a notch. Artificial intelligence, machine learning, what even are these things? Well, the way that the term AI tends to be used today actually refers to a narrow part of machine learning. So let's look at machine learning in general, and then we will zoom into AI together. Machine learning, contrary to popular belief, is not a magical box of magic. Instead, it's just a thing labeler. It's just an approach to making lots of small decisions with data. Decisions like, is this email spam, yes or no, or how much should I bid on the next auction? Now, when a machine makes decisions, takes inputs, converts them to outputs via a recipe, and the difference between traditional programming and machine learning simply boils down to where that recipe comes from. So let's think about where it comes from. In traditional programming, of course, the programmer has to think really hard about the problem, communicate in some way with the universe, right? That's how you do it. Think hard about it, and then handcraft that recipe as code themselves. Now, in machine learning, we don't handcraft that code anymore. Now the developer's job changes to feeding information into the system, and it is the machine learning algorithm that stitches that connecting code. So that's the whole difference. And how does it do this? Well, let's see it simply with an easy example. In this example, our mission is to figure out whether we're going to like a new bottle of wine that we've never tried before. So what is the first step? Define your objective. What are you actually trying to do? What do you want the system to give you when it's operating? So what we're looking at, really, is starting with the outputs. Now, what I find quite interesting and funny, actually, is that in practice, I see teams starting entirely the wrong way around here. You want to start at the left and go towards the right. You want to start with the data you have, then you want to start thinking about algorithms and whatnot, and then finally, as an afterthought, you're actually going to think about how this is going to be used. I recommend you don't do that. Start with what you actually want this thing to give you. And there's two good reasons for it. One is, yeah, maybe you can think about any part of this space yourself, and that's easy for you. But maybe your stakeholders can't, and you need to first tell them, like, what are we actually doing here? What is this thing going to make for us? In our wine example, it's going to output a yes or a no to a new bottle of wine that we haven't seen before. Now, another good reason for sticking with the outcomes first, the outputs. And I see this with engineers, so it's something we should be cautious about. If we start thinking about the inputs and start arguing as to whether or not some kind of data might be useful or not, we might find that we have accidentally agreed to build something that's not even worth building because we've spent so long worrying about whether or not some part of it might work that we didn't even ask, is this worth doing in the first place? So I recommend start with the outputs. What do you actually want to build? And I have a neat trick that you can use if you're not used to thinking through machine learning applications. Here's what I recommend you do. Imagine that it's all a hoax. There is no machine learning. There is no artificial intelligence. There's just some island in the middle of the ocean somewhere, and it's full of my friends. There's many of my friends there, and they're just pretending to be an AI. And so you send them something like a cat photo, and they just send you back sneakily that label. If I gave you access to this island for almost free, with only one catch, that you can only explain yourself to them with examples. You can't give them explicit instructions. What would you use them for? What sort of drudgery would you cut out of your life? And as you're thinking through the answer to that question, you are coming up with the right applications for machine learning. But wait, you don't know how drunk these people are. So don't just trust them with stuff, force them to earn your trust. And in order to do that, you need to be able to say what it means to do your task correctly, what you're actually looking for. And not just on one cat photograph or one bottle of wine, but over many. How would you actually score them, especially if they're imperfect? We have to get used to the fact that on difficult tasks, humans make mistakes, so do machines. And so if it's going to be imperfect performance, which mistakes are worse than which other mistakes? How do we want to assign that score? It's kind of like thinking through how you would do your scoring in a board game. Which island would be better than which other island if both were imperfect? How would you assign that? And the person who is best qualified to do that is the person who understands the business use case. What is important for the business? So this isn't something that you would learn in grad school in an AI program. This is just about thinking through which mistakes would be worse than which others for your business and coming up with a nice way to score it. And in our simple example here, I'll use accuracy. It's a simple enough metric, why not? Though I might have also gone for some other more exotic things, precision, recall, things like that that you might have encountered. And then it's really important to say upfront, before we do anything else, what the minimum performance is that we would accept. And we commit to crushing this thing if it does not meet our performance. We won't let this island do our task unless we can prove it's good enough. And we set that bar up front. So I'm going to say, if this thing doesn't make 80% accuracy, then I opt out of wine. Maybe I let my friend pick for me or something like that. Go with the alternative option. Now, why do we set our criteria up front? Because we are human. And as humans, when we invest a lot of time and effort and love into a project, we fall in love with that thing that we've just built, even if it is a pile of poisonous rubbish, right, folks? And so we find ourselves 2 years later bargaining, oh, but the performance is not so bad. 5% accuracy is really okay. I could live with that. Now, to prevent ourselves from releasing bad things, our safety net is to say, while we are still sober, before we've fallen in love with anything, what that bare minimum acceptable performance is. And this isn't a guiding star, folks. This isn't an aspirational performance. This is that cold, hard minimum, where if it was worse than this, it just wouldn't be good enough for your business. And so you can aspire to the guiding star, but you will test against this. Now, you don't need to have any data to do this part. You don't need to have hired a team to do this part. In fact, you can all immediately now grab a pen and paper and start thinking through what sorts of tasks would you offload to such a drunk island? How would you check and score their performance? And what is that minimum that you would take for your task? So since that is the first step in machine learning, And you can all do that step right now. If anybody asks you, are you doing machine learning? Are you doing AI? You can, with a completely clean conscience, say, absolutely, yes, I am. So that's our first step. Then our next step is now to think about inputs. Machine learning is not a magical box of magic. And so it can't make something out of nothing. In order to learn, there must be something to learn from. And we haven't had any wine yet. We have no data. We can't learn if we have no data, so we will have to, unfortunately, drink wine for science. That is what we will do, so we're going to drink 100 bottles of wine. And then we are going to do, once we've collected data to learn from, we're going to do the most important piece of data wrangling there is. So we're going to collect whether we liked it, an age and a review score for each bottle of wine, and then we will split our data. That's the most important piece of data wrangling. I'll explain this later, but for now, we're only going to look at the first 50 wines, and the other 50, we're going to put them in a box where no one is allowed to look at them, no one is allowed to touch them. It's under lock and key. We'll just proceed with the 50, and here they are plotted nicely for you. And our entire job here, folks, is to separate the yeses from the nos, the red things from the blue things. Can you do it? Can you do it? Yes, you can. You're thinking of putting a line? If you're thinking of that, congratulations, you have just invented a machine learning algorithm. And not just that, the algorithm that you have invented has a cool name. Wait for it, wait for it. Perceptron. Yeah, it turns out that some of the names in this space, they're a little more sci-fi than maybe they deserve. So if you were feeling intimidated by artificial intelligence, don't. Quite often when you look into the concepts, they're actually pretty cuddly and approachable. So in step 3, we are going to use patterns in our data to make recipes. So we're going to grab Perceptron and his cousins, pick an algorithm, and what the algorithm's job is to look at the data and figure out where you might like to put a nice separating boundary. And those boundaries don't have to be straight. They can have other shapes. So you can use, for example, one line with any slope, or you can use multiple vertical and horizontal lines. That's a differently named algorithm, or a super squiggly one, which we'll talk about later. But that's the difference really between these algorithms with their gobbledygook names. It's just about the shape of the allowable separating boundary that's allowed to go through your data. And then the algorithm looks at your data and sees, based on those patterns, where's the most sensible place to put it. So let's run our first one, and here we go. There's the line fitted. I hope you see horizontal wouldn't have made any sense. And then what we get out of it is what we wanted all along, a model. A model is just a fancy word for recipe. The way we use this thing is when a new data point comes in, if it's in the red region, call it red. If it's in the blue region, call it blue. That's all there is to it, right? Not that magical, but pretty useful. So in comes a new data point, and it goes to red. Or we could have used a different algorithm, so let's run that one. We get a completely different model, recipe. Now in comes the same new data point, and that goes to blue. Uh-oh. We've used two classic, perfectly respectable algorithms that any textbook will tell you are a great fit for this situation. Both of them got 100% on the 50 data points that we used to fit them. They both made all the red go to red and all the blue went to blue, so that's 100% accuracy. Perfect performance in both. And yet in comes a new data point. One says we'll love the bottle of wine, the other one says we'll hate it. They can't both be right. One of them must be lying. Who is the imposter? How do we know? Well, for that, we test. Blind trust, my friends, is a terrible thing. You must never blindly trust that machine learning is magically awesome, that you just ran some great algorithm and it's done. Force it to earn your trust. And the way you do that is you check whether it does what it's supposed to do on new data. Because the whole point of this is for it to succeed on making decisions on brand new data that it hasn't seen before. Because if you've already seen it and you know what the answer is, you can just look that up. Look that up in a lookup table. But in the new situations that are kind of like the ones that you've had to learn from, but they're not identical, a new bottle of wine, That's what we want to see it succeed on. And luckily, we have held back some new data that this thing couldn't contort its solution to. And so now we check, does it do what it's supposed to do? And why do we have two sets here? And a great analogy for this is for you to think about how you would test whether a student of yours, if you were a professor, whether a student has learned. Or what you would want to do if you want your student to learn as well as possible. So maybe you're teaching your student calculus. The training set here is the examples that you give the student to study from at home. Or that you work, it's the ones you work with the student in class. Then, the test set on the bottom there, that is their final exam. And that is where you're going to see how well they've actually learned the general task. Because presumably you don't want them to just memorize the examples you did on the board, you want them to generalize a little bit, right, to what's on the syllabus. So those are going to be relevant examples to what's on their syllabus, what they're supposed to learn. And they're only going to be able to do that test on those examples one time. We statisticians, I'm a statistician by training, we will shout at folks saying, you cannot use a test set more than once, and people roll their eyes and like, oh, pedantic statisticians nagging us again. Let me say that to you another way. If you give the same student the same final exam 2 times, do not trust their performance on the second time around. So that's a one-shot thing that allows you to know how well your student has actually done. So what's the middle bit for, the validation set? That is their at-home practice set. Because if you just give them this stuff to learn from in class, and then you take them straight to testing, you might find out that they don't understand and you fail them, and that's great, and everyone feels bad, and you correctly figure out that your student hasn't learned. But you give them no opportunity for redemption. You give them no opportunity for checking their understanding and trying again. That's why, to give them that opportunity, you have this interim, softer, you don't have to take it as seriously set, where you let them, in the comfort and safety of their dorm rooms, try their understanding on some new examples, and if they don't like how they're doing, then they can go back and read the in-class ones again, and then try their understanding on some newish examples. And of course, because they're going to iterate, at some point, you can't really trust them if they call you at 3 in the morning and say, give me an A+, all my validation examples have passed, right? You know that they might have contorted their understanding to both. That's why you say, that's all good and well, student, I'm only actually going to trust your performance on the test set. But we've given them a chance to improve by having these multiple goes with the validation set. That's why you split 3 ways in machine learning. And how does the testing actually work? It's as easy as, I know what the answers are on this new data. I apply the 2 different recipes to this new data. Of course, we get different predictions because it's 2 different recipes. We've got the truth. All we got to do is compare the truth with the predictions. That's it. And do you have a favorite here? I sure do. I'm liking the performance on the one that's doing a little better, but let's not just take its word for it. We need to be sure that we've actually had enough examples to know that we've passed that 80% bar that we set at the beginning. And so that means we're going to do some statistical hypothesis testing. You bring in your statistician, and your statistician will check and see whether you are actually clearing your bar in a statistical sense. So testing here is what keeps you safe. If you design your testing well, you make sure that you test on data that's relevant, that's like the data you need to perform in later, that there's enough of it, then if your model works, you find out in testing that it works and you can trust it. If, of course, you test it on completely irrelevant things or things that are too easy, you shouldn't trust it. Testing is your basis for trust, and it keeps you safe. If you have a model that doesn't work, you find out and you don't launch it. And it's actually really easy to do this testing because you're just comparing outputs with outputs. That's the kind of thing that's in Stat 101. Your stats intern can do that. As long as you have the discipline to know that you need to split the data and you need to keep that test set fresh and appropriate. So applied machine learning then is much, much easier than most people think. Because look, what you're allowed to do now is tinker, dabble, play, have fun. It doesn't really matter if you don't understand what the differences between those algorithms are, because you can just try them all, see how you're doing in this interim test set. If you don't like how you're doing, you go back and try a whole bunch of other things. And you don't really need to understand how it works. But what you do need to take really seriously is when you have one that you are in danger of launching, test it properly and make sure it actually does work. And take that really seriously. So I think there's a lot of misunderstanding as to which parts are sloppy and which parts are rigorous. I think it's worth spelling out. You really don't need to know how to derive the algorithm in the first place. What you need to know is how to test carefully. And so I almost suggest for developers, instead of having a working understanding of exactly how each algorithm runs under the hood there, instead, why not consider having a good knowledge of how long it takes to try each algorithm? And then the ones that are fastest to try, hey, it doesn't cost you much, just try all those first quickly on your data. And the ones that are a little bit more intricate to change up the code so you can shove your data into them, those you leave for later if the easy ones aren't working. But do test properly and carefully. That's what keeps you safe. And it sounds like there should be a catch here. It's almost too good to be true. Just tinker, dabble, play, and then easy statistical test at the end. What is the catch? There is one. In order to get away with this, you need to have enough data for 3 respectable separate data sets. And until fairly recently, it was hard enough just to scrape together data for 1 decent data set, never mind 3. And that's why you had statisticians like myself, really cautious, nervous, twitchy even, around properly treating 1 data set where we have to also communicate with the universe, set up all our assumptions at first, and so there's all these things about distributions and all that, set up our assumptions blindly, and then on the same data set, on 1 data set, do some contortionist mathematics that fits and tests in one go. Well, that's kind of hard, actually. That's what you want the graduate training for. But when you have the luxury of multiple data sets, you essentially burn the first one to tinker, dabble, play, and have that set up the assumptions for you automatically. You don't have to worry about that. If you're wrong about what this algorithm says about how the world works, you find out immediately, you try something else. It's great. It's amazingly freeing. And for those of us who grew up initially on small data and had to be very nervous working with only 1, this is an incredible freedom. You realize the power of having enough of it to split and waste some. That's what's really driving this machine learning revolution. That's the machine learning philosophy in there, that you can now get your algorithm to do that first part for you by having data to burn. So what is machine learning? It's an approach to making repeated decisions. It involves algorithmically finding patterns in data, using these to make recipes that deal correctly with brand new situations. So what's AI then? I said that the way that the term is used today tends to refer to a narrow part of machine learning. It actually tends to refer to something that technically would be called deep learning, but folks are using the words interchangeably. So when you hear AI, what's being referred to? Well, let's look at the tasks that people are getting excited about when they say AI. Tasks like recognizing what's in an image, having a human-sounding conversation, playing games that require intuition. What's common among these tasks? Well, here's our handy diagram again. And when we do these tasks, you and I, we take in information through our senses. And we get the answer as if by magic. You just know that that's a cat. How do you know that? Can you tell me what you did with each pixel to get that answer? Well, think about that. What did your brain do with the pixels? This task is easy for you, though. And if you were to try to handcraft a recipe, handcraft some code that takes you from left to right, how would you write that code? That it guarantees that you find the cat in every photograph where there is one and identify that there isn't one when there isn't one. That's really hard to do. And are you sure that whatever code you're thinking of writing would handle this? And yet for you, this is no sweat. You just do it. You can even see it's the same cat. So that's the key to these tasks. Those instructions are going to have to be really complicated. And your brain has the benefit of eons of evolution. It just does this. The task is easy for you, but you don't know how your brain does it. So how could you possibly express those instructions for a computer explicitly? You're stuck. You can't solve this any other way than to try to get a system to learn from data. You just cannot handcraft these. So these are tasks where the instructions are ineffable. And I like to say that machine learning, AI, they are about automating the ineffable. Automating tasks where you cannot handcraft the code. So AI can succeed at really complicated tasks that programmers can't write by hand. So let's set some expectations real quick. This is a personal belief. I have a very positive personal belief about my species, us, that we're smart things. And if we find ourselves resorting to AI, we can only get the task done, only get those instructions written by learning them from data. We can't do it some other way. That makes me think that maybe that's because those instructions are really complicated. It's not a matter of check whether the pixel in the top right-hand corner is blue, okay, that's a cat. And so if those instructions are really complicated, when you expect to look under the hood and read that recipe and see how is it actually working, what you're going to find in there is a rat's nest of stuff that you can't understand. That recipe is going to be too hard to wrap your head around it. My guess is if it were easy, if it were something simple, trivial, you could have found a way to write that code. So if you're resorting here, it's because you had to. And so when we think about, oh dear, I couldn't possibly trust AI because I don't understand that recipe, well, you're getting a really complicated task done. You shouldn't really expect to understand that recipe. And furthermore, if you believe that you can't trust something whose decision-making you don't understand, why would you trust a human? You should never trust a human because a human can never tell you how they make decisions. That would involve them saying how each neuron in their brain was activated in sequence. And no one ever tells you that. You can't explain why you chose or didn't choose to have a cup of coffee today in terms of your blood sugar levels and the electrical and chemical signals going on in this machine learning algorithm that we have right here. And yet, it doesn't bother us. And it doesn't bother us that a student can't explain how they do the calculus by explaining things about their neurobiology. Why? Because we test them. We don't mind that we don't know how we work. We check instead that we do work. Don't just take the calculus student's word for it, test them. And similarly, while you won't be able to read this recipe, test it carefully. Look at the inputs, look at the outputs, and make sure those things are connected in the way that you want them to be connected. And that's really what we mean when we talk about the kind of AI explainability that we want. We want to be able to do what humans also do. Look at the inputs, look at the outputs, and make sure that those inputs go to those outputs in a correct way. Not how, not what the sequence of neurons is on the way, but that it actually does work, and that it works in appropriate data. Now, if you're going to make these really complicated recipes, you need more. More what? more sophisticated algorithms, more data, and more computing than for these straightforward things like fit a line through some wine data. And until fairly recently, this was science fiction. And I'm talking this decade recently. I'd like to introduce you to three amazing colleagues, three amazing Googlers whose work contributed to changing all that. So in the realm of sophisticated algorithms is Geoff Hinton. Now, Geoff spent his entire career studying and loving artificial neural networks. And this is quite something, actually, because the fashion in machine learning statistics was against artificial neural networks. If you've ever heard of AI winters, that had to do with the entire field kind of getting discouraged and thinking this was entirely a waste of time, but not Geoff. Geoff kept at this. And when an entire field is discouraged, they're also not building the hardware that you would need to efficiently work with these things. Let me explain very briefly. Deep learning refers to deep neural networks. What are deep neural networks? Well, sounds like it vaguely has something to do with the brain, but it's more like layers upon layers of mathematical operations. And deep means more than one layer. Because when these things were named, the idea that we would have enough computing power for goodness, 2 layers was too much to dream. So 2 would be deep, and any more than that would be deep. Today they're all deep. Today they're all more than 2 layers. It's layers upon layers of mathematical operations. And the promise here is if you have enough computations in each layer and enough layers, you could, in theory, subject to excluding some mathematical perversions, you could, in theory, fit any shape boundary you wanted through your data. So you're not just putting a line, you're not just putting a series of lines, you could sign your name in cursive between those red and blue regions if you felt like it. Very flexible algorithm, the most flexible algorithm available today. So this is the one that's going to succeed if the others fail. Except, there's a catch, nothing's free. It takes a lot of computing power. And that's the basis for these constant disappointments. Yeah, the promise is there, yeah, they'll work, except the beastly amount of computing power that would have been required just wasn't available. So people would get excited and massive disappointment. And so after all these disappointments, no one is explicitly making the hardware to get this done. Except some folks, Geoff included, noticed that a completely different industry just happens to have made the hardware that makes training these things efficient. And that is all of us playing video games. And that's why you hear GPUs this, GPUs that in the context of deep learning and artificial intelligence. It just so happens that this hardware is really good for a completely different task. So the realization is kind of like, yeah, if I grab one of these GPUs and I hack that thing, I get an AI supercomputer for $300. And with that realization, suddenly, the promise of this super flexible algorithm that was out of reach before, it got delivered. That's kind of the start of this AI revolution. Now in the realm of data, I'd like to introduce you to Fei-Fei Li, who is Google Cloud's chief scientist. And Fei-Fei, at some point, was thinking about why is it that computers are just so much worse than a human 3-year-old at this game of cat, no cat. And so she did a back-of-the-envelope calculation and thought about how much data a human 3-year-old must have had, effectively, to be able to learn labeled data, high-quality labeled data. And she realized that we're talking order of millions. Aha, says Fei-Fei. Of course computer vision researchers aren't going to make great progress using a few thousand images. You need millions of beautifully labeled images. Okay, great. So I just have to grab that. Who's got that for me? Turns out nobody. Because Folks love their kids a lot more than they love their computers, and they spend their time labeling things for their kids. No, honey, that one's a dog, that one's not a cat. And who's doing that for computers? Well, turns out you can think of Feifei as mother not just to her kids, but also to computer vision. Because Feifei took this upon herself to make beautifully labeled data sets using, at some point, something like 60,000 Mechanical Turk workers to look at images and label what's in them. No computer, honey. This one is a car, this one is not a bicycle. And her project, she open sourced so that everyone could make progress in computer vision. When ImageNet, this project, launched, it had millions of images as required, and suddenly progress could blossom. And of course, because she is chief scientist at Google Cloud, she is also a driving force behind us making sure that we have nice, beautiful, large data sets on all the classic AI applications at Google Cloud. And then finally, in terms of the hardware and computing, these things are still computationally expensive. And if you're going to do it the naive way, it's going to take too much hardware and cost too much. So, you could train these algorithms in any language of your choosing, in theory, subject to your level of masochism, I guess. But just might take a really, really long time and cost too much. So Jeff Dean, who is our sort of resident Chuck Norris, if he does a push-up, the world moves, we like to tease at Google. Jeff is the driving force behind TensorFlow, a project that we open sourced, which makes those calculations efficient. So what it feels like to a data scientist, it feels like any other package. You put your data in, you kind of arrange the thing first so that it accepts your data, you hit run, out comes a model or recipe on the other side. Not that special. But what's special is how it actually does the training under the hood so that things that would have taken you ages before can be quick, efficient, and cheap. So with those three breakthroughs, I'm happy to report that the future is here. And now you can actually use AI for real business applications. Let me show you some. It's not all cat, no cat, though if you insist on cats. This is an actual screenshot of my phone where I put the word cat into Google Photos, and here I get a whole bunch of my pet cat Huxley. And that's being driven by deep learning. But our customers also use it for other applications, like Airbus is in the business of making high-quality satellite image maps. And it's not high quality if it's covered in clouds. So you got to remove the clouds, you take multiple shots, and you have to remove the cloud cover, except the snow is working as intended, the clouds we don't want. How do you figure out what's cloud and what's snow? It's hard to do by eye. I don't know if you would want the job of having to do this pixel by pixel. Maybe it would be better if AI could identify regions that are probably cloud, as you see there, and suggest that for workers, so that the workers have an easier time removing things. Communication, so text to speech, speech to text, that's all powered by deep learning, as is idiomatic translation. Now, I don't speak Chinese, but from what I understand, this is not a word-by-word dictionary lookup. This is capturing meaning. Automating drudgery, I know how we like to do the same thing over and over, including write those things in our emails that are hello whoever, the same thing, how are you, lots of times. Wouldn't it be better if we could just save ourselves the time if we just had an option to pick something that we do often if it's useful to us, or just keep writing if it isn't to save time? That's driven by deep learning on Google Cloud as well. And it's pretty popular. Turns out that we put quite a lot of repetitive stuff into our emails and can save a lot of time by cutting that out. Playing games, so it's game playing AI, same kind of idea. And this looks kind of frivolous, but turns out this is related to the math that runs those self-driving cars. We at Google like to make sure nothing goes to waste, so that actual game-playing AI We took pretty much that, very similar, and we gave it something else to do. Instead of information on the state of the Atari game, we gave it information on our data center. Instead of a score, we gave it energy efficiency, and instead of a joystick, we gave it control of the cooling systems. Now, before, when you take the more classic data science analytics approach, where you have people, Googlers, looking at data centers and profiling how you could run the cooling system more efficiently, you got like a 1 or 2% energy efficiency increase. That was incredible. And, you know, a huge reduction in carbon footprint, a lot of money saved. When we let the AI do this, what do you think the improvement was? 1 or 2% is good for a human. Around 40%. That is huge. That is amazing, and it's great for the planet. So, pretty cool applications there, and there is so much more that you could do with it. As long as you have the data, the algorithms, and the computing power and software to make it all work. And to make sure that you do, we at Google Cloud have your back. Instead of having to build your own data center that's going to run these things, borrow ours. And instead of having to reinvent the wheel and make those algorithms, those packages yourselves, just grab ours. We're building cutting-edge ones for you, making them all available. So all you need to do is try them all out, put your data in them, and see what works. And I know how you really wanted to by hand label a whole bunch of cat photographs, but say that's not your cup of tea and you don't want to do that, a million of those yourselves. We have those big, rich, beautiful data sets that you can just borrow from us and use. And so, steps to success as you're starting out with AI. The first thing is define success. Think through that drunk island analogy. Think about what you would actually build and which mistakes are worse than which other mistakes. And you can do that right now with a pen and a paper. You don't need to hire anyone. You don't need to get anything fancy. So that's on you to figure out what you would like to use this for. Then the next steps, we can help you prepare your data and try out a whole lot of different algorithms really quickly. But important, this is still on you. Make sure that you actually test those solutions on brand new data, because the proof of the pudding in machine learning is in the eating. If it works on new stuff, on relevant new stuff, that's like what it's supposed to handle in real life, then it works. So make sure that you save some data, put some data aside, and actually check that it's doing what you need it to do. And then use your solution to transform your industries. So I hope you are excited. Your AI adventure awaits. Thanks so much.